Okay, great. So thanks everyone for attending and thanks for this opportunity to share my accumulated useless knowledge of MPAS framework with people who might actually be interested. So the goal of this short lecture is just to give an overview of the framework of MPAS and especially parts of it that aren't particularly well documented and just kind of orient new users and maybe some existing users to different aspects of how MPAS was developed and organized. And I'd also invite, Zyler and Adrian and others who've been working with MPAS for as long as I have to feel free to jump in if you have anything to add or if you need to correct anything. Okay, so I thought I'd start with a little bit of the history of MPAS and how we got to where we are now. So, and some of these details might not be exactly right, but I did my best to try to reconstruct this. So, the model for prediction across scales was spearheaded by Todd Ringler at LANL and Bill Scamrock at NCAR around the year 2010, following the development of the so-called TRISC discretization scheme, named for the four authors shown there on the right. And the vision was a shared framework for building geophysical fluid models based around an unstructured global variable resolution Voronoi grids. And MPAS is not restricted to global variable resolution Voronoi grids, but that was the driving force behind it. And this predates E3SM by quite a few years. So this kind of shared framework vision was before E3SM existed, and DOE was still primarily working with the NCAR CESM model, and MPAS was kind of envisioned as the next generation variable resolution component models. And so it initially started with the ocean model and the atmosphere model. So the ocean model developed at LANL, and the atmosphere developed at NCAR, both of which are still developed out of those locations. There was also a shallow water core, which was more of a demonstration core. And then later, the sea ice and land ice, now MOLLE cores, were also added. And I should also point out that in MPAS terminology, the word core is usually meant to refer to one of these physics components. Okay. And then I thought I'd give a little history on the repositories because the people working on the code in the hackathon may find they actually need to look at some of these older repositories to get a full picture of the history of certain files. So we originally started with a Subversion repository and I actually looked it up. The first commit was in March 4th, 2010. And then a few years later, we migrated to a Git repository, which originally was completely private. And that's this MPAS dev MPAS repository. And I believe this Git repository includes all of the SVN history for what it's worth. And then a number of years later, and I didn't look up the dates, this was maybe 5 years ago now, we migrated to a second Git repository called MPAS Model, which is maybe familiar to a number of people, and that was entirely public. And it had a continuous Git history with the previous repository and was at the time a submodule within E3SM. So the entire MPAS code was a submodule. And if I remember right, this was the main motivation for switching from a private to a public repository. But because there's, 4 or 5 different component cores in MPAS, and not everyone wanted to go public at the same time, that's why we ended up with 2 different repositories. And then most recently, as of about a year ago, oh, it's almost tomorrow's the anniversary, I guess, of 1 year of ditching the Git submodule and inserting the MPAS code directly in the E3SM repository, which has been a huge benefit for code integration. And working with the other component teams in E3SM. So one unfortunate side effect of that transition is that the older history before this date, is not easily accessible from this repository, and it's easiest to refer to the previous repo if you want to see history before that. There is kind of a workaround where you can see the history past this conversion date on individual files if you do like git log and then a file name. But if you just do git log in general, it won't see past this break. If people have questions about that, I can try to explain those idiosyncrasies, but I don't want to get too distracted. And so when we migrated to this E3SM repo, we created, the E3SM data directory structure has a different subdirectory for each model component, like the atmosphere model, the land model, etc. So there's a directory for the ocean model, for the sea ice model, and the ice sheet model, but there's also an additional component for the framework itself. And so that's a little bit unique in E3SM. And then the individual components link to the framework library that they all share. And so you'll see a number of different components / MPAS directories, one of which is the framework. And then as of now, we're still primarily developing Mali in a fork of E3SM at the Mali dev organization, but it's a fork of the E3SM repository, so it has the exact same layout and we can merge things back and forth. So that's just kind of a minor note. So any questions about either the history of MPAS or of how the repository is organized right now? Okay, great.
If there are quick questions, I would also mention that I've been playing around with navigating this history on GitHub itself, so from E3SM back to MPAS model and back to MPAS. So if people run into issues where they'd like some help figuring out how to figure out when some original choice was made, that's important. Just get it.
And I guess I'll reiterate that if the hackathon ends up digging into some pieces of the framework, like the registry parser and things, a lot of that code has not been touched in years. And so the relevant Git history log or the relevant commits may actually date back to any one of these three early repositories. So in the core code, you rarely need to go back that far, but in the framework code, it's pretty mature and there a lot of files haven't been touched, in 5 or more years.
Matt, can I ask a question?
Sure.
So I'm trying to understand what's the difference between the MPAS model being a submodule within E3SM and then being a component. So is that the pure difference between those two? Is that mainly the existence of shared library?
Well, it's just, Holly, it's like how we added the sea level model as a submodule to Mali.
Yeah.
So if it's a submodule, it is a standalone repository in its own right, but it's, accessible to the parent repository as opposed to having the code be directly part of the parent repository.
Right.
So it mostly has to do with the workflow for bringing in changes are a lot more complicated when you have submodules because you have to commit them to the repository itself and then go to the parent repository and update which hash the submodule is pointing to, and there's a lot of opportunities for things to break or be inconsistent.
Right. Thank you.
Sure. Okay. And then I thought I would summarize a little bit about the kind of philosophy that went into developing the framework and where it originated, because I think that helps explain some of the idiosyncrasies of this piece of code, which I think is rather idiosyncratic, and a lot of people get kind of caught up by it. and find it intimidating. And I think that's for good reason, but I also think once you kind of understand where it's coming from, hopefully it will be less intimidating to just dive in and kind of try to understand pieces of it as needed. So the concept of this shared framework was to have things like data structures, mesh operations, parallelization, input-output, parsing of the configuration files, timekeeping, and any other physics agnostic operations in one shared piece of code that all of these different component cores could utilize, so that each model isn't rewriting all of these kind of basic shared operations. And I would say, I guess I said this in my lower bullet point, but there is this philosophy to have everything in MPAS framework be very general, to not be specific to any of the physics cores that are using it. And it which makes it very flexible, but it also perhaps makes it more cumbersome than necessary for any specific application. Like, for example, in an ice sheet model, your time unit could probably just be years. Like, we never actually care about, or we might care about days. We probably don't care about hours, minutes, seconds. But by using MPAS the MPAS timekeeping module, that includes years, months, days, hours, minutes, seconds, and so we have a lot more granularity than we care about, and there's additional cost to that complication. But the flip side is we didn't have to write any timekeeping code. So just kind of understanding that there may be features that you think are relevant to the model you're working on, but they may be supporting some other model in a general sense. So that's kind of how it ended up looking the way it does. So the framework itself, so many people have contributed to MPAS in general, but the framework is almost entirely written by two people. One is Doug Jacobson, who was a postdoc and staff member at LANL and left for Google. Well, he worked at Intel for a while and is now at Google. He left about 5 years ago. And the other was Michael Duda, who is like a software engineer at NCAR supporting the MPAS atmosphere model. And so I think a lot of the way framework looks reflects their coding style and their coding interests, for better or worse. And one of the kind of overarching goals there was a desire to make use of modern software features. And again, remember, this is about 10 years old when this was put together. But things like templating, operator overloading, classes. But there was also this tension at the time of the project wanting to stick with Fortran due to the familiarity of the domain experts with Fortran. And so that kind of dual goal led to there being a lot of, I would say, custom implementations in the way these modern software features were implemented. And I think there's some challenges in long-term maintenance. There's somewhat unusual Fortran code. There's both C and Fortran code in places where the Fortran only implementation wasn't going to be sufficient for the need, so they added C code in a few places and things like that.
And I would just quickly add, there's C code that generates Fortran code. That's an especially unusual feature, I would say.
Yes, and and related to that, there's an executable that runs during the build process, which is also kind of unusual and has led to some complications getting the code to compile on some supercomputers. And as of when I looked the other day, there was about 73,000 lines of Fortran code and framework, plus an additional 1,800 lines of include files defining derived types, and about 10,000 lines of C code. So it's pretty intimidating. So I added this link to documentation, and for the most part, I think the coding standards in MPAS have been pretty good at making sure things are well commented in MPAS, with the exception, ironically, of framework itself. So the codes in each core I think are well documented with comments, but framework itself has very few comments, which is very challenging for those of us who didn't write it to go in and understand what's happening. There is some actual documentation, but again, it's not great. This first link goes to an old repository we go for documentation. And there's a user's guide, which many of you have probably seen. There's a developer's guide, which has some useful information, but it's very outdated because it hasn't been updated since 2013. And then there's also these design documents for framework features. And some of those are quite useful, but there's only a handful of them, and some of them and even some of those are somewhat out of date. But I think it's worth remembering that these things exist and these are good resources to look at, and you might get lucky in getting your questions answered there. This I pulled from the developer's guide, and I don't want to go into too much detail, but there's a number of conventions that MPAS has adopted to make it more to keep a cleaner implementation of having these multiple cores in a shared framework. So each core has a name and an abbreviation. So if you're working in ocean code, you're used to seeing OCN in file names, or for land ice, it's LI, and sea ice, it's SI. Um, and there's a specific convention to naming subroutines to prevent namespace conflicts. So that's described here. So you would have like, they all start with MPAS and then have the core abbreviation and then the name of the module. And then we use all lowercase with underscores for module and subroutine names. However, variable names are using so-called camel case. And there's this tendency for variable names to be very verbose and descriptive. So you often have very long variable names with the hope that things are easier to read and it's easier to understand what a variable means. And then I think that's the main things to point out here. Just those coding style conventions are listed here, but they're maybe not as visible as they could be for new developers. Okay, so getting into the actual code itself, this is the structure of the MPAS framework source code. And as I said, this is a subdirectory. It's basically its own component within E3SM in components MPAS framework. These first three are symlinks to the actual component code. That's not really important for this discussion. This core shallow water and core test are kind of generic demonstration cores that were used a lot for testing and developing framework features that were independent of the cores, but I don't think anyone's actively used them in a while. So ignoring all that, I've kind of summarized what the main features are. So the driver is a standalone driver. E3SM uses a different version in each components directory. And external are some libraries that were chosen to be useful for MPAS framework. And these are basically frozen versions of external libraries, and these are rarely, if ever, touched. So we have a frozen version of the ESMF timekeeper and a parser for XML format for our IO streams layer. And then framework is kind of the main event. This is where most of the basic MPAS functionality lives. Operators are shared algorithms that are not core specific, like geometric operations mostly. And then tools is the other place that will be relevant to the hackathon. These are parts of the framework that are not built into the MPAS executable. So you can kind of think of them as pre or post processing So there's this input gen tool that generates the default nameless and stream file every time you compile the code. And then there's this registry directory that includes a parser of registry files. And this is what Zyler was mentioning has C code that writes Fortran code that is then compiled when you compile MPAS itself. And so I think for the hackathon, if the initial emphasis is on like a C, anything related to free or C compliant time dimension, most of that work will be in framework and in this registry directory. Any questions about this? Comments? Okay. So I'll have a couple slides kind of describing how registry works. So it's a XML file that defines all of the dimensions, nameless options, stream definitions, and variables that the model you're building will be using. And the idea is that you define them in a simple XML format, and then there's a parser, which I mentioned on the previous slide, that will convert those XML definitions into Fortran and a little bit of C code. So to avoid tedious duplication of, having to write, duplicate routines for every single variable, for instance. And the way kind of the high level data structure for variables is that there's this concept of a var struct or a variable structure, which is a grouping of model variables. So I have one example here where a var struct Halo exchange test includes a whole bunch of different individual variables. You can also have a var array, which is a collection of variables that are related to each other, and they would be a member of a var struct. There's not very many variable arrays in the code, but they're kind of critical for things like tracer advection and things like that, where in the code, it looks like a high dimension array, but in the input and output, each rank of that array actually is a variable with a meaningful name. And then kind of at the lowest level, we just have a plain old variable, which, something like XL or thickness or whatever. And so they're defined in this XML syntax. And then this on the top here is just a little more detailed example. Var structs can have multiple time levels. Var arrays and vars can have a number of different attributes, and this just shows an example. But I've listed down at the bottom here the list of attributes that are currently supported. So for every variable, name, type, which would be like integer or real, and dimensions are required. And then all of these other attributes are optional. And so if the hackathon is working on things like long name or other CF compliant attributes, they would likely need to be added to this list of supported attributes. And that list of what is supported is defined in this file, source tools registry, registry.xsd. And so I think that would be the first place to look if there is a need to add new attributes beyond these existing ones.
So Matt, I will just mention really quickly that I believe there's another one called missing underscore value, and that's going to be important for us as well.
Okay, that's interesting. I didn't see that in the code, but you're right. So it's possible either I missed it or it's in a slightly different place. So that might be something to keep an eye out for.
If it's not there, that'll be an early thing for us to fix.
That would be ironic if missing value is missing.
It would be.
So I realize I'm pretty much using up my half hour at this point. I have a number of slides on internal data structures, which are kind of analogous to the var structs, var arrays, vars in registry, but internally in the Fortran code are handled differently. And I don't know that these concepts are going to be particularly relevant to the topics in the hackathon, so I may just kind of go through this really quickly. But basically to point out that we kind of each instance the core has kind of a master data structure called domain. And then beneath that, there's a data structure called block list, which allows you to have multiple blocks of geographic extent on each processor, which is a feature that was pretty neat, but ended up not being worth the extra complications. And so I think typically there only ever is one block, and so this block list layer is kind of redundant and could go away, but is still there in the code, so you have to kind of dig through that layer. And then you get down to the var structs that we talked about, which can optionally have multiple time levels or not. And then you have the individual fields listed within each struct. So there's also this concept of pools, which is kind of a custom data structure that Doug and Michael developed, which is similar to a class or a derived type in that each of these pools can have attributes and methods, child members, etc. But it was implemented from scratch in Fortran and includes a lot of linked lists. And again, I don't want to go too much into that, but you'll see these pools, you'll see a lot of pool accessor routines. And if you look at the pools code, you'll see a lot of linked lists. And it's basically was just a custom way to implement these multiple layers. And there was some specific reason why we didn't use derived types directly, which is the kind of native Fortran version of classes or similar to classes, and instead use this pools implementation. And I think I could talk about it if people really cared, but that's I think it's kind of unfortunate we ended up with pools because they have a lot of limitations by being like a custom implementation of a class, but that isn't supported by the compiler itself. But that's just the way it is. So those of you who've worked with MPAS code at all will see that typically you see a subroutine have a structure where you have variable definitions that are pointers for the thing, all the variables that you actually care about. And then there's a section where you're getting a subpool to get the struct that contains the variables you want. So you need this custom MPAS pool get subpool call. And then you need to pull out the actual array you want from the struct. And so there's an additional set of MPAS pool get array calls that actually fill in these variables. And so you end up having multiple steps just to access a variable, which is a little bit awkward and makes the code longer than it otherwise might need to be. And then a few notes that is probably common knowledge for people who've worked with this code for a while, but may catch new people off guard is that the pool routines, because they're using quoted variable names, are case sensitive, even though Fortran is not. So however this capitalization was written in registry is what has to be used in the get array call here. And if you don't match it, then it won't find that item in the pool and you'll get an error. And then related to that is that typos or trying to retrieve a variable that isn't a member of a pool cannot be detected at compile time because this isn't a built-in data structure of the compiler. This is a data structure that was customly written. And so you only get an error at runtime, which is, in my thinking, a major limitation of this data structure. And you also have to compile with debug equals true for the error message to actually be useful. So I don't want to talk about this, but this is just an example of, this is the pools data structure, and it has a bunch of kind of child members that are like data structures for each type of variable as well. So there's a lot you can dig into, and you may need to. Okay, so I think I have a handful of more slides. Is that all right if we go over a little bit, Zyler?
So here with me. So.
Yeah, that's fine. No,
Okay.
thanks, Matt.
Yep. So now I'm actually going to talk a little bit about the code that's in source framework. So as I mentioned a number of slides back, framework is often used generically to include, and I'll just go back, to include all of this stuff, anything in the MPAS-framework directory. But framework also could specifically refer to just the parts of the larger framework in this framework directory, which is the basic MPAS functionality. So I'm going to talk a little bit about this specifically. So this is the contents of that directory, and you can see there's both .f files and .inc files. So .f is the actual Fortran code, and then the include files are definitions of derived types that relate to each module. And you can see there's a lot of different things in here. Some of these are really simple, like MPAS constants just has like the value of gravity and things like that. And it includes ifdef to use the physical constant values from E3SM if you're running in E3SM. Some of these other files, I think like dmpar, this is the parallel domain parallelization is the dmpar. This file is thousands of lines long and includes all of the MPI communication, Halo exchanges, communication lists. It's quite complicated. But I find most of the time I end up working in either these blue areas or green areas. And I think for the topics in the hackathon, that will also be the case. So the two blue boxes have to do with I/O and the stream definitions, which is how we define our input and output file lists. And there's a lot of different files for I/O. So this ends up being kind of confusing. There's a stream manager, there's stream lists, and then there's the I/O itself. And then these layers, the I/O layers, are actually then calling PIO, which is then calling either netcdf or parallel netcdf. And those are external libraries, and so these files have a lot of wrappers to those routines. And as anyone who's worked much with MPAS has discovered, you can get a lot of confusing errors related to PIO and these IO layers. So finding exactly which of these stream and IO files is causing you problems can sometimes require a lot of digging, but it's these, I guess, 9 files collectively that comprise the input-output system. And then the other thing is the timekeeping module, and that I find comes up a lot. And I have just a couple more slides to talk about timekeeping. So a lot of you probably know that xtime is the most fundamental time variable to MPAS, which is a string of this year, month, day, hour, minute, second format. And actually, there should be 2 lowercase m's there. I just didn't type it correctly. So that's the time variable that framework is expecting to exist and considers kind of the master version of anything related to model time. Each individual core, I believe, now has something like days since start or days since start time or something like that. which is a real variable with units of days, which is a lot easier to manipulate than this string variable. But days since start is not actually recognized by Framework or used by Framework. That's kind of a thing that each individual core has added optionally. So I said X time is the most fundamental time variable. However, you can't really do many operations on this string format. So actual time manipulations or operations are done using what's called an MPAS time type, which is really just a very thin wrapper to the ESMF time data type. And as I mentioned earlier, MPAS has its own version of a frozen old version of the ESMF timekeeping module in the MPAS source code itself. And then I wrote here that when you're compiling an E3SM, I think MPAS actually then uses the ESMF version, the timekeeper that E3SM is using, but I'm actually not positive about that. So that might be something that needs to be determined. And this MPAS time type slash ESMF time type handles year, month, day, hour, minute, seconds as, distinct components of a time. And it includes different calendars, like whether or not you have leap years. And it has overloaded mathematic operators so that you can subtract two instances of this time type and get an interval that represents the duration of time between them. So it's important to understand that there's the concept of both a time, which is a distinct point in time, and an interval, which is the duration between two times. And that's a concept inherited from this ESMF time type. Oh, thanks, Rob. Rob pointed out where the E3SM version is. And then the MPAS timekeeper also has concepts of a clock and an alarm. So a clock would keep track of the current time, but you can have alarms set that will ring when the clock reaches certain times. And this is used extensively for knowing when to do I/O. And I think it may also be used to keep track of when to synchronize with the E3SM coupler. So I added a note here that if one of the goals this week is the addition of a CF compliant time variable, this may indeed require adjusting some of these timekeeping routines or possibly looking into if the version of the ESMF timekeeper needs to be updated. I don't remember when this frozen version is from, but I would suspect it's 5 or maybe 10 years old. And it hasn't caused a problem that it's that old, but it's also possible that there are features that are not accessible that would be useful to have. Okay, I guess this is my last slide. And this is just pointing out the MPAS timekeeping types. This is the include files. So this is not the entire file, but just kind of pointing out we have this generic MPAS time type, which is really just wrapping this ESMF time type. So then you need to go look at the ESMF time module to see what the pieces of the ESMF time type are. So it would have things like years, months, days, and all of those individual components. And then when you try to do like subtraction of 2 times, it's internally, converting years, months, days, and all those individual units into some compatible units that it can do operations on. Typically days, because days always have a fixed number of seconds in them. So days and seconds are kind of the fundamental time periods. Whereas, like years, each different years will have different numbers of days or different numbers of seconds in them, which is the complicating factor. And then on the right is the actual timekeeping module. And I just listed all of the subroutines it contains. There's also another about a dozen functions. So it's not just subroutines, it's both subroutines and functions. However, in practice, I find most of the time I need to do anything or modify anything, it's in one of these 4 routines that are getting or setting either a time or a time interval. And so I think it's kind of worth skimming through these 4 routines just to kind of understand roughly how they work. And again, pretty much all of these time routines are wrapping corresponding versions in the ESMF time manager. So yeah, I think that's my last slide, and hopefully I hit on some topics that are going to be useful this week, but I'm happy to answer questions now or as things get going if there's specific details that will be useful to people.